Good afternoon, everyone. I am Sezin. I'm studying aerospace engineering at RMIT University. So today I'm going to talk about my project, which is a novel concept for geostationary debris orbit measurement. So I'm going to start off with the problem we have with the space debris, and then I'm going to explain what I've done in this project in relative to the debris problem, and then I'm going to briefly explain all of my simulation results and calculations. So I'll start off with a movie clip from Gravity. So this clip demonstrates how dangerous the space debris are becoming. So this is LEO, and I'll just give you a quick run through what LEO is. LEO is the low Earth orbit, which is 160 to 2,000 kilometers from the Earth's surface. And Geo is geostationary Earth orbit, which is about 36,000 kilometers from the Earth's surface. So the space debris are building up in both the LEO and Geo. So you can see it's becoming quite dangerous. So in the near future, we have to abandon all of our space missions. We can't send any more astronauts or even the satellites into outer space, because this is what's going to happen. So, yeah.
Can you do something about George Clooney?
So, I'm going to explain Kessler syndrome. Kessler syndrome is actually a scenario in LEO where the density of the object, the space object, becomes so high that the collision between them could cause a chain reaction and causing and generating more debris and initializing further collisions. We don't want that to happen. And I've already given a quick run through about Geo and LEO. So this is a simulation from ESA. What might happen in approximately 2055 if the space debris keeps building up like this. You can see the ring, the blue ring and the red ring shows the density of the space debris or the space object. So here is another clip which shows the collision of Iridium satellite with the Cosmos. This event took place on 2009, and it itself created approximately 2,000 more debris in LEO. Yeah. So yeah, and most of the debris were more than 15 centimeters larger. That's what we detected. But there were also millions of other debris formed due to this event. So, in the next slide, I've got a graph which represents the debris in LEO. So, two big events took place. One is in 2009 because of the Iridium satellite and Cosmos collision, which created a lot. Almost you can see it was right. So you can see it was 13,000 before in 2010, and due to this event, it drives up to 15,000, so almost like 2,000 more debris formed. And there was also another event when the Chinese government blew up one of their own satellites, creating a lot of debris in space. And that was back in 2007. So here is what I'm going to show what happened with the space debris before 1957. So there was no satellite, no space debris, no space object. In 1960, we started to put satellites in LEO, but not in Geo yet. In 1970, you can see satellites and space debris building up in Geo as well. 1980, 1990, 2000, 2013. Okay. So you can see a high density of debris. Some of them are actually active satellites as well. So, but you can see the density of the space object is becoming higher. So what are the problems? So if a Kessler syndrome occurs, we are going to lose almost more than 3,000 operational satellites, which means no satellite technology, means no GPS, no mobile phone, no internet for us. And yeah, we don't want that to happen. And these are all the social impacts. So among all other countries, Australia would be highly impacted because Australia is a huge country with a small population, which heavily depends on the satellite technology like GPS and mobile phones. So yes, the debris in LEO are a concern for us, but the debris in GEO is also important because the geostationary satellites are very expensive to place. We need a lot of fuel to place a satellite in GEO because it's 36,000 kilometers from the Earth's surface. And they are also precious because we have limited amount of slots in GEO to place the satellites. So my project is mainly based on GEO. So this is the concept. So how are we going to do the position measurement of the space debris? So the concept is, we got the Gaia star. So the Gaia is actually a space mission, astrometric space mission, which can measure the position of the star up to 0.02 arcseconds of error. So I'm calling this a Gaia star because Gaia knows the position of this one. And then we got the debris here. So we know the debris is moving at 15 arcseconds per second. So at their closest point, when they come at the closest distance to each other, we're going to take a snapshot of them, and then we're gonna measure the distance between them, and then calculate the position of this space debris, because we know the coordinate of the Gaia star. So we know the distance between them, and we can easily find the coordinate of the space debris in relative to time. So is it feasible? Yes, it's feasible thanks to Gaia and adaptive optics. So as I've mentioned before, Gaia is an astrometric space mission which can measure the position of the star with an accuracy of 0.02 arcseconds. And then we got adaptive optics here. So adaptive optics gives us a small error, small position measurement error, because the value of the full width at half maximum is really small, and it is related to this equation. As you can see in the equation, that the position measurement error is directly proportional to full width at half maximum, and full width at half maximum is actually the spot or the centroid. And so it's important because when we are measuring the position, we actually measure the centroid mainly. So here's a comparison between the image of noise without noise. So this is what I got through the MATLAB simulation, and you can see the one with no noise gives us no significant distortion, and it's very smooth, and yeah. And you can see the centroid which is at the center, is actually very clear, whereas you can see here it's a noisy image with lots of distortion because I applied the quantum noise in here. Error budgeting. So the error budgeting is actually analyzing and calculating the factors affecting the position measurement error. So there are lots of factors. One of them are anisokinetism, which is the air turbulence. So you can see in this graph, which is the anisokinetic error versus the guide star. So I took a separation of 5 here. So at the separation of 5, we get a value almost 20 milliarcseconds. Calibration error. So the calibration error is the error relative to the pixel coordinates and the pixel size. So the timing error. The timing error is really important because we know the debris is moving at 15 arcseconds per second. So it's important we know the timing error, and the timing error is related to the GPS system. So theoretically, it was supposed to be 14 nanoseconds, but practically it was recorded as 100 nanoseconds. And the field distortion error. The field distortion error is the error of the optical element. It could be some kind of shape error, like a bend while manufacturing. Position measurement error. So this is one of the most vital measurement errors. And there are 2 factors affecting the position measurement error, which is the number of photons from the background star and the number of photons from the satellite debris. position measurement error. So I actually validated this equation through MATLAB simulation. So you can also call it multi-carbon numerical simulation. So I ran the MATLAB code 1,000 times in a for loop, and I got 1,000 centroids. And I also generated 1,000 values for, this is sigma pos. Sigma pos is actually the position measurement error here. So I got 1,000 values numerically, which I compared with the value theoretically. Theoretically is the one that's in the formula. So you can see the mean value of the 1,000 value were 0.0416 pixels, that is the numerical value, compared to the one which was 0.0418 pixels from the theoretical value. You can see the values are very close to each other, which validates the formula here. So comparison between the formulated data and the numerical data. So I got a table here with different number of photons, 10, 100, and 1,000. And I've compared the value of the position measurement error. This is the formula, that's the theoretical one, with the numerical value. You can see the values are really close to each other, which validates the formula. And this graph further validates the formula because you can see the green curve shows the position measurement error, which was the theoretical value, and the blue one is the numerical value. You can see they're nicely superimposed with each other. So it validates my formula even further. Results and calculations. So this is the big table of the results which I had to work out. So these are all the error sources and the position errors. So anisokinetism, which I've shown before in the graph. We found at separation of 5, we found the value to be 22. The timing error, that was the 100 nanoseconds, which I converted it into milliarcseconds. Astrometric error, that is from Gaia, which was 0.02 milliarcseconds. Calibration error is the design requirement, 3. Field distortion error, 3. And the position measurement error, that is the number of photons from the background star and the satellite, which we found 4. It's relatively smaller than what we expected, so that's a good thing. So, and the total residual sum of squares, we found it to be 23.18. So you can see the dominating error source here is actually the anisokinetism, which is 22, and the rest are pretty good. And just in case, I should mention, the residual sum of the square is actually the square of all these values, which I did a summation of, and then a square root of them. And 23.18 milliarcseconds is actually 3.82 meters. So in conclusion, we can say that this technique works because I've proved it, and it could be used for the position, for the measurement of the position of the debris with an accuracy of 23 milliarcseconds. And this technique is actually 40 times better than the current technique. So during the study, I've established the error budget, and as I've shown before in the table, that the anisokinetic error was the dominating error, followed by the position measurement error. And we found the measurements down to magnitude of 15 to be possible. So that's pretty good. And I would like to thank Northrop for sponsoring me and my supervisor, Transfer Results. And if you're interested in knowing more about the position measurements and stuff like that, you can contact me. This is my contact address. Thank you for having me. Any questions below?
The quantitative simulation, what variable did we send? Like, did you change the number of photons in each group? What are the variables?
Yeah, I changed it. I gave a range of 10 to 100 with an interval of 10, and then from 100 to 1,000 with an interval of 100. Yes. So they're different. Yes. Yes. Yeah. So like I just wrote a code in the MATLAB, and then they did the computer did the simulation. So yeah.
Do you know what kind of techniques they currently use to do tracking of debris?
Yeah, I was expecting that question. So yeah, they, as far as I know, they use small arrays of telescope, and yeah, I don't know much further because it wasn't related, but yeah, that's about it. That's what I know in my knowledge.
You might want to hope that Craig's hanging around for drinks afterwards, you can ask him.
So what's the visible size of objects that are within your, or in this one at Geo?
Oh, sorry.
So how big is something that you could, how big is an object you can be before you can detect it?
How big it is before you can detect it? I'm actually not sure about that.
So what's the limits of the system you're working on? What's the
Yeah.
limits of it?
The limits of it?
So how small can you see?
About what square meter?
Yeah, maybe we have to work it out. Any more questions? Yeah, maybe everyone's tired.
Well, thank you very much, Leila.
Thank you.
Thank you.
It's okay.